Here's our final answer. Let's just plug it in. Our final answer is psi of g. The psi, I won't say g because I'm not talking about the general function. I'm talking about that function explicitly. All right? Psi of x and t equals, yeah?
Negative, can you go from negative infinity to positive infinity?
Yeah, minus infinity to positive infinity of that stuff. So 1 over the square root of pi a times sine ka over k times e to the I kx minus omega t dk. Okay? Now, this still requires you to do an integral, right? And it's not so obvious what it is. Do you agree? It's not obvious. So like here we have this nice picture. Here's my x space, here's my k space. All right? And it's really not obvious at all what's going on here with that problem. And by the way, so the cleanest problem is one of the homework problems that I gave you. The cleanest problem is homework problem 2.22, which is what you should be doing from now until next Tuesday. All right, and what 2.2 does is it gives the psi, the what total psi at t equals 0, to be a Gaussian. All right, so that psi at t equals 0 is a Gaussian, and that turns out to be the easiest problem that you can do, like with this free particle stuff. And it has some other magic properties too that we'll talk about. All right? But it's not obvious what this thing is yet. All right? So what we're going to do is we're going to look at some limits and see if this makes any sense whatsoever. Okay, so let's look at some limits. And one thing to do, let's first look at the limit of when...
Tuesday?
What's that?
Tuesday?
What?
We're going to look at limits?
I have a minute. So, well, let's look at the limit. That a equals small. And in the limit of a equals small, psi of k equals 1 over the square root of pi a times the sine of ka over k. And what can we do if a is small?
Just equals k.
We can take the small angle approximation. And the small angle approximation of sine theta is theta. So this becomes 1 over the square root of pi a times theta is ka, right? Over k. And so that becomes so that equals the square root of a over pi. Right?
Yep.
Okay. So look what we just did. Let's look. Here we go. Here's the x space representation. And that's x. All right? And here's what we've got. We've got psi. And let's write it at t equals 0. So we're just going to look at the t equals 0 part. Now, what if we... This function was confined between minus a and plus a, right?
Right.
But what did we just make a?
Really small.
Really small. So in other words, what we're saying is this is the original problem. Right? Minus a to plus a?
Yeah.
So, do you guys agree that's what it looks like in x space?
Yep.
Okay. Now, let's now transform this into the k space. So this is k. And now up here, this has to be little phi of k.
Yeah.
All right? And what does a little phi of k look like as a function of k?
It's
Well,
not a function.
we're making this approximation.
Square root of a over pi is just
Square root of a over pi. And is that a function of k or is that a constant?
constant.
It's a constant. So in other words, from minus infinity to plus infinity, 5k equals square root of a over pi.
Don't you lose k there at the sign?
Oh, the
Small
small n approximation is sine theta for small theta is equal to theta.
Right.
So
Just makes sense.
So
K.
just ka is theta. Nice, huh?
Can you do that? Is that legal?
Of course it is. You do it in elementary physics when you solve for a simple pendulum.
I mean, what if K was huge? What if the wave?
But when K is huge, it still has to be the same as when K is small.
Yeah,
I mean when A is small.
Can you do that? though?
K is a single number, so
K to be
K
zero.
over K is,
Yeah.
K is zero, you get infinity.
I mean the actual process.
Yeah,
I'm
but
just curious, that's all.
yeah, but see,
Whenever you cancel a K, it can't ever be zero.
but when I take it, I mean, look, when I look at small a, it certainly produces this thing when the k is canceled.
But to cancel K's, you can't do it if K
Well,
can be zero.
if we're taking the limit and we can
With a
always
going to
assume
zero.
A is going to zero, we can assume if we have to, we can take the limit by L'Hopital's rule. And the derivative
It's
of
through
those K's
zero with
will
a
be 1.
equals zero.
Yeah.
It's through zero with a going to zero, and it's legit. All right? Okay, but Jet,
Well, we
let me
can-
get the last point now.
Yeah, we can force those K's to be 1s.
But what's so important about this k space? What does this say? This says all k's contribute, right?
Yes.
So what else do we know about k? What is, for example, is our p operator?
I
Equals minus I h bar partial with respect to x. And like p on a wave function, if it's an eigenvalue, what are the eigenvalues?
En.
No, of p, they're h bar k.
Oh, H bar K.
Okay? Right? So p's, the momentum, are h bar k's. So k space is k space, but what is it also?
Momentum space?
It's momentum space. So multiply k's by momentum. All right? Now, what does it say about this little problem? As I shrink and shrink and shrink and shrink and shrink and shrink my original free particle into a tiny initial place, what does it tell me about my momentum that represents that particle?
he gets
It's
infinity.
infinite.
The momentum can then be any value of k minus infinity to plus infinity. All right?
It can be anything.
So this is kind of a representation of the uncertainty principle.
Right,
Delta
it's the
x,
uncertainty.
delta p, greater than or equal to h bar over 2.
It's very
That when you start to have less and less and less uncertainty in x, you're certain you're confining that particle into an incredibly small amount. What happens to your uncertainty in p?
You can't find.
It becomes infinite. You can't localize and say what p really is. And what does this represent? That physical state, where the p is unlocalized. Right? So, that was an important part to get to. In Griffiths, he looks at the opposite case. Guys, what will happen if you let A go into infinity?
There's a graph of
What do you think is going to happen over here? It's going to localize P. Right? But that's why the whole idea of the x space representation and the k space, let's now call it x and momentum space representation.
So for the whole thing where you can find a particle position or momentum at every.
That's right. That's exactly what we're seeing. And these things represent real particles. Real free particles.